Hello and welcome. Some time ago, I got interested in geometric algebra, but I wanted a book about its applications, and quite frankly, this is the cheapest one. So I decided to buy this one. And the first part of the book is dedicated to geometric algebra, and then it gets into the electricity and magnetism. And I forgot so much of that stuff. I just can't. I couldn't follow it. So I said, okay, I got to start back on E&M. So I had so much luck with this book when I decided I wanted to study the calculus, the Student's Guide to Vectors and Tensors by Daniel Fleisch. And I said, hey, I'm going to see what else he's got. Well, what do you know? He's got this excellent book, A Student's Guide to Maxwell's Equations. I bought it. I've been doing some of the problems in it. It's really good. It's a lot of fun. And I was doing them on, just pencil and paper. And I said, hey, I'm going to type some of these up. And if anyone likes them, I'll do a whole bunch of them. But let's see how it goes. If you like them, let me know. If you don't, then I'll stop. Okay, so the book begins with Gauss's law for electric fields, and it's in two parts. The first part is in the Gauss's law in the integral of the form, which is this. So it says the total electrical, the flux, is equal to the surface integral of the electric field inner product with the surface, the normal, the vector, okay, times the small increment of area. So this is all equal to the total enclosed charge divided by the permittivity of free space epsilon naught. Okay, so all of the homework problems in the section 1.1 have to do with this equation. All right, so here's all the stuff I just said. Okay, so here's the very first, the problem. Find the electric flux through the surface of a sphere containing 15 protons and 10 electrons. So I don't know what the hell that is, but it's kind of funny. Oh, so he just wants you to do the total enclosed charge, the sum of all of the charges. So you got 15, the positive, the charges. So this is the charge of one of them. You got 10, the negative charges. You take the products, you add them together. Now you have the total enclosed charge, and you got to get the answer. He wants the flux, so you got to divide it by epsilon naught, and you get this number. Okay, so that was kind of boring. All right, so now we're into some juice here. This is fun. So a cube of side L contains a flat plate with a variable surface charge density. So that's the key to this, variable surface charge, the density. And he gives you this, the density rho is equal to minus 3xy. So when you see a function like this in these problems, you know you're going to integrate it because you're in chapter 1, which is in the integral of the form, and he gives you the plate extends, he gives you the limits of integration for x and y. So the question is, what is the total electric flux through the walls of the cube? Okay, so he made a nice little drawing here. So this is your plane, your surface, and he gave you the function of this density. And so equation 1.16 in chapter 1, you'll find this equation. The total enclosed charge is equal to the integral, the surface integral, of the density, the function, times the incremental, the area dA. And he gave us this, so he's just looking for a double integral. All right, so we got the double integral x and y of minus 3xy dx dy, because that's our area, that's our dA, right? So here's the function he gave you, and this is our dA, x and y. All right, so we integrate x, we get x squared over 2, put the limits in, we get L squared over 2. Now that's a constant, we pull that out front, so we're just left with the integral of y dy from 0 to L, and we pick up another 2, so it makes that a 4, we get a y squared. We put in our L, so we're left with this. The total enclosed charge is equal to negative 3/4 of L to the fourth But now that's not what he asked for. He asked for this, the total flux. So you just divide that by the permittivity, and this is the answer. Now, all of these problems in this book, he has a website, danfleisch.com, maybe danielfleisch.com, and you pick out the book that you bought and you go there, and he lists the problems and the solutions. What's fun about it is he also will let you do hints. So he'll say hint number 1, hint number 2, but you can see the solutions of these problems, which is actually kind of cool. But obviously, you should try to do them yourself first, or otherwise, there isn't any point in buying the book, right? I'm trying to relearn this stuff after being away from it for decades, something like 40 something years. Okay, here's another one. Find the total electrical flux through a closed cylinder containing a line charge with a linear charge density. And once again, we have a variable charge, the density, but this time it's linear. Whereas up here, remember, it was planar. So we were doing a plane. Now we're just doing a line. So he gives you the function once again, and he gives you the limits of integration. So it's very obvious what you should do. You need to integrate this from 0 to h to find the total enclosed, the charge. So we put in our function, which is the lambda naught 1 minus x over h, and our L is x, right? Just dx. So we integrate that, x squared over 2, from 0 to h. We put in our limits. We do this arithmetic, and we get lambda naught h over 2. Now, once again, he's asking for total flux. So you put that you found over epsilon naught, and that's the answer. Okay, here's another charge density the problem. What is the flux through any closed surface surrounding a charged sphere of radius a naught with volume charge density? Now remember, we've done a surface charge density, which is area. We've done a line charge density. Now we're going to do a volume charge density. And he gives you a function where r is the distance from the center of the sphere. All right. So what is the flux through this variable charge density as a volume? So in the book, he gives you equation 1.117, where it's the total enclosed charge is the volume integral of the volume of this function times dv. Now here was where I got stumped. Okay, what's dv? Well, the hints he gave here is this is a sphere. So I said, oh, then that must mean we want the dv in spherical coordinates. Yep, and sure enough. Okay, well, how do you do that? Well, it's a lot of work. You have your transpose from xyz to r theta phi are given by these equations. You've seen these before. They're used in everything. Well, to get this volume, I had to look this up. I did not know this. I had to look it up. And I did it by hand. It's awful. I didn't actually do it all by hand. I'll show you. I'm getting excited. Okay, you write down your the Jacobian, the matrix for the transpose. So you have to take the partial derivative of all of this with respect to all three variables. So you got x across here, y, and then z, and then r, and theta, and then phi. So you have to take all those partial derivatives, you put it in this matrix, and the way you get your volume element is you take the determinant of this. Now, that's where I went to an online, the matrix calculator, and did it. I wasn't going to do that by hand. And the determinant was, it was actually the non-negative. That's why they tell you to take the absolute value, r squared sine theta. So the volume, dv, is the determinant of that Jacobian times, instead of dx, dy, dz, is dr, d theta, d phi. Okay? Now, I had to look that up. I didn't know it either. So that means he wants us to do a triple integral. Now let's think about this for a second, where these limits come from, right? So the theta is the polar angle which goes from the North Pole to the South Pole. So it's traveling a distance of 0 to pi, right? The phi is the equatorial angle, which is going all the way around the sphere. So it has to go from 0 to 2 pi. So that's where and he gave us this limit, A naught, R 0 to A naught. So that theta is going from 0 to pi and phi is going from 0 to 2 pi. Did you ever notice on math and physics, the forums, that the mathematicians and physicists do the opposite with these angles? That this one is phi and this one is theta. Why do we do that? It's so annoying. Anyway, I digress. Okay, so here's the way I used to do triple integrals because I make a mistake, and I even make a lot of mistakes. I busted them up. So I put like with like, and I would start here. So the integral of d phi is just phi. We go from 0 to 2 pi. We pick up a 2 that goes out here with our constants. Now we got to do theta. The integral of theta is negative cosine from 0 to pi. All right. Now I got tricked here the first time I made a mistake. I had to go back and figure it. Was that the cosine, right? You're taking the limit. You just can't ignore the 0 like normally you do because it has a value. So you got the cosine of pi minus the cosine of 0. Well, this is a -1, and this is a +1. So it's a negative of negative is a positive, and a negative of negative is a positive. So this actually becomes 2. So my answer kept coming out half of his answer because I didn't pick up a 2 here. So it's 2 times that 2, you pick up a 4. Okay? Now we just got to, the only thing left is r cubed, which is r to the 4th over 4, 0 to a naught. This time the 0 really is a 0. And we get pi rho naught a naught cubed. Excuse me. And once again, he's asking for total flux. You divide by epsilon naught, and you got your answer. Okay? So the only thing hard about this one was figuring out what he's asking for here in terms of dV, because this was not well described in the book, or I didn't think so. Okay, I'm only going to do one more, and then I want your feedback on whether this is worth doing or not. I think this one's the most fun, actually. A circular disk with the surface charge density, okay, so this is a surface, and it gives you a number, is surrounded by a sphere with radius 1 meter. If the flux through the sphere is this number, what is the diameter of the disk? Does that make sense? Well, what he's asking? All right, so let's look at what we got. And we know this already. The total flux is equal to the charge enclosed divided by epsilon naught. So he said the flux through the sphere. So this is the total flux, right? So we can find what? The charge enclosed. Just take epsilon naught to the other side, multiply this out, we have a number. Okay? And from equation 1.3 in the book, if your charge density is a constant, like this is just a number. As before, the problems we were solving, they were functions, right? They were variable charge density. Well, this is a constant charge density. So there's no integral. It's just the density times the area. So now we can find the area. It's just the total enclosed charge divided by the density. And we have these numbers. We just did them. So the answer is this, the meter squared. Now let's go back to the question. What is the diameter of the disk? Well, now we have an area of a disk. Well, what is the area? It's pi r squared. So we can get r out of that, which is the square root of that. We get this. Well, then what's the diameter? Well, it's 2 times the radius. So this is the answer. I thought this one was the most fun, and it took me a long time because I had to really think it through. Okay, so once again, give me some feedback on these. If you like them, I'll do more. If you don't, I'll shut up. All right, thanks. See you later.